All right. Hi, everyone. Thank you for joining us for today's webinar. It's titled Food Production Automation Starts with AI Vision, Not Robotics. My name is Jessica Schnobrick. I'm a marketing specialist for the Association for Advancing Automation, and I'll be serving as your moderator today. As a reminder, attendees viewing this webinar are in listen-only mode, which means that you are muted. If you have questions, please submit them in the question panel or in chat, and we'll try to address as many of these as we can at the end of the program. We'll also have a Calendly link in the chat if you would like to schedule an appointment directly with our host. This webinar is brought to you by the Association for Advancing Automation, also known as A3. A3 is the leading automation trade association in the world for robotics, vision and imaging, motion control and motors, and industrial artificial intelligence technologies. We are the hub for all your automation resources, products, partners, new applications, trainings, and information on the latest technologies and innovations. Visit automate.org to learn more. And thank you to this webinar's sponsor, vCortex. vCortex from Occipital AI is a revolutionary all-in-one AI vision solution designed to transform how manufacturers deploy and scale machine vision. It combines our cameras with three critical capabilities in a single solution: robust vision model management, an intuitive no-code application builder, and a dynamic real-time analytics dashboard. And with that, it's my pleasure to introduce today's speaker, Anthony Romeo. He's the product management manager at Occipital AI. He has 3 years of experience and brings over a decade of expertise in machine vision. He holds a computer science degree with a focus on artificial intelligence. And I'll hand it over to you, Anthony.
Thank you so much for the intro, Jessica. Thank you so much, everyone, for hopping on. I'm excited to talk to you about Occipital AI and our product vCortex, and really why it makes sense to deploy vision first when you're starting off in automation. So a little bit of background about Occipital AI. We are a small startup a little bit north of Boston in the Massachusetts area. We have a team of about 40 people, and we started off as a spinoff from the Soft Robotics group, and we really wanted to focus on machine vision and specifically AI vision. With that focus in the AI vision space, we have really focused with food manufacturing. The reason being, I think that AI vision enables itself to highly non-repeatable parts, and the food space just lends itself to that organic, natural variability. We've been around for a little bit now, and we've actually inspected over 5 million different pieces of food, different products, and we've reported to some of our customers over 80 million different unique defects that has allowed them to take action and improve their automation process. So why we're all here today, why should you use vision first when deploying automation? I think it's a really good question. I think it's something to think about. And hopefully by the end of this presentation, it'll be very clear why we should use vision first. So the world is constantly changing. Every day there's some new innovation, and there's a big pressure for everyone to automate and be more efficient. And this pressure comes from various competitors. If you're not moving forward and everyone else is moving forward a lot faster than you, you can fall behind and lose market share, really scary. When you're trying to raise funding, it seems like everyone wants a 2 times their investment within a year, very quick money. Other companies seem like they can offer that. So again, there's this pressure to automate and be able to leverage higher returns. There's also just, again, with AI being so transformative and so many new AI products constantly being released, it's really changing everything. And what was efficient and worked yesterday doesn't necessarily work moving forward. And with all this pressure and all of these unknowns, where do you even start with automation? It's not an easy thing to get started with. It costs a lot of capital to get started with automation, and it's not exactly clear and can be very overwhelming on just exactly where to get started and where is going to make sense for your ROI. I've preached a little bit about how AI is changing everything, and why does it make sense for us to use AI in the food automation space? Well, I think traditional machine vision has been around for an extended period of time and is really good and really reliable when it comes to highly repeatable parts. If you've deployed an automation solution, you'll probably hear some questions of how fast is the belt going? Is it left or is it right justified? How much space is there between products? What's the index between them? All of this is really good at having the product be in the same place every time. We look at our iPhone, we know the dimensions, we know there's a screw going in this exact corner. We do it on to the next one. If something doesn't look exactly right, we can reject it and say a defect. The thing is, that doesn't really work with food. There is no CAD file for a chicken wing. You can see that everyone here is a little bit different. And next year's birds might be bigger than this year's birds, or next year's birds might be smaller. There's just inherently a lot of organic variability when it comes to living products, which really lends itself to AI vision. It's hard to use traditional machine vision and write a bunch of rules of my chicken wing is going to be between this length and that length, and I'm looking for a bone and I want a fixture pattern match. Very complicated. When you're training an AI system, you can use deep learning and provide a lot of information. And even if the system is seeing a chicken wing that it hasn't exactly seen before, it knows, I've seen so many and this is right. If you think about a young child trying to learn what a house is, you can try to give the child rules. Oh, a house has between 1 and 10 doors and 18 windows and is 1 to 12 stories. But a kid might see a shed or a mansion or a hotel. And is that a house? Is that not a house? Really, the way we train our kids to learn these things is we say, this is mom and dad's house. This is our neighbor's house. This is grandma's house. And when the child has seen enough of these houses, they have this model in their head of what a house is, and they can see something completely new and know that's a house, even though I've never seen that one before. So with this pressure to automate and with AI vision finally being ready for food, what are some things to be cautious of when you're deploying vision and automation in general? Well, lighting and environmental variables are a huge impact. If you've deployed machine vision and a cloud comes through or a shadow gets cast, all of a sudden the system starts giving bad detections. It gives false negatives, false positives, and it can't identify the difference in pixel contrast because of the shadow that we're casting. Another thing is poor part presentation. I talked earlier about how we need everything justified and indexed. Food manufacturers will deploy these singulation machines, which vibrate a ton and introduce a lot of noise. And it's very loud. It's very high maintenance. It's very annoying. It's a very big footprint in your facility. And all of this is in an effort to just make it so that the food is presented one at a time, singulated and justified. It's also tough when you deploy a system and you have some poor planning and you spec'd in a white conveyor belt with some company, and all of a sudden things change and you can't procure that white conveyor belt, and now it's a blue one. It's challenging because the product has never changed. It's still the same product, but because of the way traditional machine vision systems are trained, it's going to really struggle with a different type of background. And then finally, just a litany of integration issues. Your camera isn't talking to your robot, and you call the robot company and they say, our stuff is all good, it's the vision company. And you call the vision company, they say, our stuff is all good, it's the robot company. And you're kind of in the middle, like, well, I'm using both of you. Who can help me out and get this working? Because it's not working as advertised. Well, I think that all of those shortcomings are addressed with our product vCortex. And I think it really leads to starting with vision and getting an understanding of your application to then be able to scale and increase automation moving forward. The toughest thing is to deploy automation when you're not ready and don't exactly know what's going on. And you've just taken a problem that you try to fix with automation, and you've now scaled that problem across your entire system. So I think slides are getting a little bit boring. Let's get some action and show you our software. So the vCortex platform, we are training using synthetic data generation and deep learning. So a lot of existing AI companies will say, hey, we have this awesome product. It can do anything. You just load in a couple images, you train it, and you're good to go. The challenge with that is you might be able to get a cool demo with a couple of images, but in reality, you need much more than a few images to get a robust object model. It's not going to be able to cover a ton of edge cases with just 10 to 100 images. The other issue with hand labeling these images is the fact that you introduce a huge human error component. If I have to label 100,000 images of corn and say, draw a little bounding box around the corn, say this is piece of corn number one, this is piece number two. If I want to go watch the Celtics game and it's 6 o'clock on a Friday and I want to get out of there, I might speed through and the data integrity is getting lost on that labeling. Or if we have a new person that's coming in that we've just trained up, they might have a difference of opinion on exactly how to draw the bounding box around the corn and what counts and what doesn't. At Occipital AI and with our vCortex platform, we take all of that guesswork out of it. We don't want to be labeling images either. What we do is we take a full 3D scan of the product and marry 2D and 3D data. So here you can see a piece of corn that we got. We went to the store for one of our customers. We bought the corn that they have, and we took a full 3D scan, and you can see we know everything about it, the reflectiveness, where we have some husk, where we have corn, how long it is, the circumference here, the circumference up here. All of the dimensional information about this corn we have without needing to have someone go in and manually label it. We will take a scan of a representative number of products, trying to capture both good and bad products. And what we can do is generate an asset library of different 3D corn models. You can see here's the bad one. The front has a bunch of this tip fill. The kernel's kind of falling off. Yuck. So once we've taken a scan of maybe 20 or so pieces of corn, again, we can just go to the supermarket and buy these because no one in the food space has an IP on corn. We can use synthetic data generation to quickly train our models. So instead of deploying a vision system, capturing 100,000 images, hiring some poor intern who has to go label those 100,000 images, instead, we will scan 30 pieces of corn, 30 pieces of product, and then we'll say, hey, we know these 30 pieces of corn. Let's generate a scene with 20 of those 30 pieces of corn, and let's do it again, and let's do it again, and let's do it again, and let's do it 100,000 times. Instead of someone going in and manually labeling them, we're saying generate it so we know how many pieces of corn are in there and where they're all going to end up and settle. So here we'll say we have a lot of corn. They're going to be overlapping. We'll use a blue conveyor belt, and we've got good lighting. And here we can see our data generation. And voila, we have a bunch of corn falling onto a conveyor belt, a blue conveyor. Our physics engine is going to let this settle. And now, instead of someone taking this live image and labeling it, because we have these corn assets and we know how long they are, we know each position of this without having to hand label because we generated it. It's not a random scene, it's a scene that we've created. We will do this hundreds of thousands of times to generate our model. And again, it's not a person labeling. This can run off in the background. We hit go and it starts processing. Now, I talked earlier about some areas where vision falls in automation. And one of the things was poor project planning. So maybe you go through, and another thing I mentioned was the lighting environment. So two huge things we can touch on here. If your lighting changes, or if you have to respec a conveyor belt with traditional systems or new AI systems, you either need to start retraining the traditional vision system rules, or you need to acquire another 100,000 images and start labeling. Yuck. What we can do is we can say we still have the same volume of corn, still going to be a lot overlapping. We actually deployed a white conveyor belt now, and we have a really dark environment. It's undersaturated light. We can hit go, and now we are biasing the model with darker images with a different conveyor belt, and we can hit go and have this train and deploy this object model in a matter of weeks, whereas other systems take months minimum. So this is, again, very powerful, and it's future-proofing your investment. Should anything change, the corn assets that we scanned, those aren't changing, right? Maybe the corn is a little bit variable, but again, because we are using deep learning, we can account for that organic variability. If the conveyor belt changes, we have to run another model, which takes some time, but again, it's days for us to spin up a model and can get it to you as soon as a week. Whereas other systems, you have to hire an application engineer, you have to acquire more images with the new conveyor belt, you have to go in and label those images. It's a whole mess. So a couple examples of different products we've worked with. Again, for us to generate a model, we just need to get it in-house and start scanning so we can generate these models very quickly. And when a model is working and deployed, you can see here we have our little Capri Sun juice boxes. It's looking for ones that have the straw and the label facing up. If the label's facing down, it needs to get sent back and rejected so it's the right orientation for when we're packing. And if you have a kid and you have given them a juice box without a straw, you can understand the crying tantrum that is about to ensue. So we want to make sure that these guys go back, get the straws so that all the product we're going through is good. We can also, I talked about things not needing to be indexed. We can just have a bunch of bulk things on a conveyor. Here are kibbles and bits. And with this bulk, we can identify the kibble from the bits. Can also do classification and identify a litany of different products. Here we've got our donut detection, identifying glazed donuts, Boston cream donuts, crushed donuts. Really, if you have a product, we can scan it and we can start inspecting it very quickly. So once we generate the object model for you, we hand it off to you and you are good to go. Let's stay logged on here. So once you're deployed, what are you going to do with that data? Why does it matter? Here you can see we have chicken breast deployed. It's been going, looks like their shift started at 5 a.m. and going all the way until now. We can also look at how many of each defect we're seeing and at what time. So when people want to get started with automation, a lot of people think, I want to get a bunch of robots in there. I want every robot picking everything. I want vision and inspection. And that's awesome. And I think that is the future of where we ultimately need to be. But it's really smart to make sure that you understand your process so that when you are deciding how many robots do I need, you can make an informed decision. So here, we could have a robot that, yuck, low trim. We don't want that getting to the customer. Could deploy a robot arm that goes, picks them up, removes it, and we solve that quality issue, no more low trim. We could also, with the data that we now have, do a little bit more of a deep dive and go in and say, all right, looked like it was good. Oh, what happened at 8? We had a huge spike with low trim here. In reality, we probably don't need a robot grabbing these. I think that the blade of cutting the chicken went bad, and then we replaced it and that defect started falling off again. Instead of deploying robots, which are very expensive to go and pick these off, if we had just known, oh, we just need to change the blade upstream in our process, it saves a lot of money, it saves a lot of time, and it de-risks a lot. So we can use the vCortex system to send alerts and interface with upstream machines. If we see 10 defects of low trim in a row, we can send a notification to an operation first, and we need to replace the saw blade because it's not cutting the chicken properly. If we see 10 corn dogs in a row that all have burns, we can send a system to the frying machine to turn down the oil temperature. We know that if we've seen 10 in a row, we're probably going to see an 11th, and we're probably going to keep on seeing these burns until we take some action to remedy the problem. We can also go in and do a deeper dive, not just see how many defects we have, but let's look at each individual defect. All right, we can see here, we've got the rib meat is right up here. The volume of the rib meat or the area was 593 inches squared. We only had one instance. The total volume of the product was 15,000 inches squared. And we have all of this information for every chicken breast. We can differentiate between the fat and the rib meat. Here we can see that there were 2 pieces of fat it detected if we go in and look at our subparts, we can see the individual areas for each of those two pieces of fat. So all of this is really powerful for ensuring that your food is safe, ensuring that customers don't get bad defects, and it just allows you to optimize your process again. If we can see, oh, we had 1,000 pieces of chicken that were identified as low trim that were all really close and probably were fine, we can maybe change the tolerance on what is classified as low trim. If we're picking up the chicken and we're bruising it as we grip it, and we see, oh, the average area of all of these pieces of chicken is smaller than we thought, we can change our end of arm tool so that it is better for gripping the product that we have. In addition to going in low trim, we can quickly navigate. We have wrong side. If the chicken is membrane side versus muscle side, the nasty side that when you flip it over from the supermarket, you don't want to see face up, yuck. And again, we have all of the dimensional information for every piece we inspect. If we go to the overall product summary, these are not defects, these are good pieces. We can see a aggregated histogram of all of the product that we inspected. So right now we're looking at from the start of the day, 12 a.m. until currently. And we can see in that time period, there were 2,129 pieces of chicken that were between 6.15 and 6.58 inches. All of this is completely customizable. If these dimensions mean something to you of maybe it's a gram of fat is too much versus not, you could have 2 bars on how much has that gram of fat versus how much doesn't. All of this displaying too is based on this calendar. If I wanted to not just see today, but I wanted to see last week, if we hit apply, all of these boards dynamically update based on the time that we have here, which again, really led us to dig in and troubleshoot. So you can see here, we have a nice little pattern. It looks like stuff ramps up, then it dies down, they close for the day, and that was the same pattern throughout the week. We can zoom in if we want to say, oh, what happened here? I really want to take a look. We can drag and zoom in. And again, having all of this information is going to allow you to make a better informed decision when you're trying to scale your automation. How big should the end of arm tool be? Well, we can use the products that we have to better inform that. How many robots do I need to deploy? Well, we can look at our throughput, how much product we're seeing. We can use that to drive how many robots we need. So again, everything in here is very powerful, and we're trying to give visibility on how you can make an informed decision when automating. Now, this all sounds great. We build the object model for you, we scan the product, we hand it off to you, you can see all this data, that's great. But a question a lot of you guys might be wondering is, well, how do you know what is high trim versus low trim? Like, I'm in the food space, I'm the expert, I know my application better than you. And I would say I agree. We don't know every application exactly what's going to be needed. So what we've done is we've given our customers the ability to tweak everything very easily without needing to be an AI expert. All of the AI model creation is on the occipital AI side with vCortex. We do all the training. When it comes to using that model, we enable the customers to be able to use it too. So here we have a system that is looking at chicken breasts, and we can see in this upper right, this is our grasp selection. So it's going to send coordinates to the robot to pick these, and it's going to go 1, 2, 3, 4, 5, 6. And we can also see down here, we have one, this guy is the wrong way. It's the muscle side up. All the other ones look good with the membrane. And then we've got 2 pieces of chicken that have low trim, big fat chunk here, big fat chunk down here. Now, someone might say, hey, this guy up there, that looks like a pretty big chunk of fat. Like, why is that counting as good chicken? Why is that not counting as a defect? Great question. So we can go into our recipe, we can edit it, and when we go into our inspection rules, we can see that for the system to classify a piece of chicken as low trim, it needs to have a minimum fat area of 1,000, or it needs to have a minimum rib meat area of 1,000. This does not impact the object model at all. The object model is going to look down at the chicken using the 2D and 3D sensors. It's going to identify the dimensions of that chicken. It's going to use vision to figure out where the defects are of that chicken, but it is going to get a dimension value of the whole entire product and each defect that it sees, or each subpart, in this case, fat. So if we go to our pick view, we can see all of these pieces of chicken. We have different dimensional information. We have the confidence score of how confident we are it's a piece of chicken. We have the XYZ location. I can click on a piece of chicken. And again, I have the dimensional info. I have the robot position. I can go into the inspection and I can see the total area. And I can also specifically look at the rib meat. So for this piece of chicken here, we didn't see any fat, but we saw rib meat. And the area of this rib meat, I know it's a little bit small, but it's 925.35. So again, that's 925. Now, if you remember in our recipe, we had the inspection rule saying it needs to be 1,000. 900 is less than 1,000. It does not meet that requirement for low trim. So again, just so everyone can see it, we have 1, 2, 3 good chicken. These two are good, with this guy in the upper right also saying good. I'm going to go into the recipe. I'm going to tweak that inspection rule to not have it be 1,000 for the rib meat, but I'm going to drop it down to 900. Now, because we have a value of 925, which is more than 900, the object model has not changed. The chicken that we're looking at isn't changed, but we can see instead of 2 pieces of chicken that are good, or instead of 3, we only have 2, and it is now identifying this as low trim. I know the low trim label is blocking it. You can kind of see the rib meat behind there is all right there. So it really enables the experts, the operation, the plant managers to go in and tweak the application for exactly what they need. If you want to have a food safety initiative and increase all those tolerances, you can do it. If you want to relax the tolerances and maybe you need to ship more product, you can relax those tolerances and you can also do it. So not only can we change what counts as a defect versus not a defect, up here we have the pick order going 1, 2, 3, 4, 5, 6. You would think that the direction of travel here would be going left to right, and we want to pick the first one before it falls off. What if our direction of travel is the other way? We actually wanted to prioritize this one. Do you have to go in and edit the code and change? Nope, super easy. We're going to go in, we're going to edit our recipe. Instead of the inspection rules, we're going to go to our sort prioritization. So right now, the system is saying when I am sending coordinates to the robot, which again, just to show that, super easy for us to send to the robot. You go in here, you configure all your tool settings, you configure, you pick what controller you want, you can set up the detection and tracking, and you don't need anything else. This will figure out how to talk to the robot. We have everything automated. So going back down to the sorting. So here, we're only prioritizing the furthest thing downstream. We don't care about anything else. We just want to have the robot grab it. We can invert it. We'll save and exit. We will reload this recipe. And now, when I go into the test view, again, same object model. It's identifying the same chicken. But when it sends the pick coordinates to the robot, they will be inverted. So now we're going 1, 2, 3, 4, 5, 6. We can also, maybe we don't just want to go a certain direction. Maybe we want our robot to just pick out the good chicken first. We can go to our recipe. We can edit the sort, and we can look for our inspection label. And what SKU do we care about? We want to grab the low trim first. and we'll disable that distance downstream. So the right side should be the first one. We'll save and exit. We will reload. And so we can see now that we wanted to prioritize low trim. And so we have 1, 2, 3, and distance downstream we inverted. So it's going to go from the right to left. So we can see, okay, first it got this low trim, then this one, then this one. It finished all the low trim. Then we went and got the other pieces. So what this allows us to do is really, really change and customize different things. We can say exactly what counts as a defect. We can tell robots exactly what to prioritize. We can prioritize the proximity to center, the height above floor. Often you'll have a robot line with multiple robots picking from a conveyor. You can deploy different pick strategies for each robot. So if you can think that you had 6 robots, 2 on each side of the big conveyor, the furthest ones downstream, you really care about this distance downstream. You don't want anything falling off that conveyor belt. So you would bump this up to the highest priority. You might have another robot that is trying to get things that are stacked. You don't want piled product on top of each other. Again, we don't need to have our stuff singulated and justified. We can have overlapping product. Maybe you want the first robots to pick the top of the pile, so when it gets to the last robot, it doesn't have to worry about a stack and am I going to get it in time. So using all of the data that we can get from our analytics dashboard, we can use this to inform how we need to set up our recipe. And then with the recipe setup and the analytics dashboard data, we can make a more informed decision on how we want to move forward with automation. Does it make sense to deploy a new cutting machine to cut the low trim better? Does it make sense to just deploy a robot arm downstream that can grab it and eliminate it? How many robots do we need? Can we get away with 2 robots? Do we really need 4 robots? Is 6 robots going to be overkill? All of this data, again, is very easy to use, very easy to parse with the Cortex platform. So coming back to our presentation here. Oops. So why we should deploy with vision first with vCortex? Well, first of all, we can deploy in weeks and not months. So it's very quick to get that ROI. They're using vision allows you to start automating. And as we mentioned earlier, there is an immense amount of pressure to automate and to use these AI systems. Starting with a low capital expenditure and an easy bite at the apple with vision gives you a ton of information for a low cost that can better inform you how to better use your capital expenditure down the road. This is also smart because investors, again, want a ROI. Having the vision to be able to show different investors the data and why your product works and how much money they can expect to save, super valuable. We own the object model creation. There's no finger pointing of who's the ML guy we need, what applications engineer do we need to get in here? Hey, do we need to contact the vision system to get someone to work on this? We own all of the object model creation. We will do a 3D scan. We will send you that object model, and then you can start working with Recipe Builder right away. And using that Recipe Builder keeps your team in control. Again, we are experts in training AI vision models, specifically in the food space. We are not necessarily an expert on how to cut a chicken or where, but we know that those experts exist in the field, and they might not have the ability to write their own software and code, but we know that they can go into our Recipe Builder settings and say, hey, this is what I want to prioritize. Hey, this is how much fat is too much fat versus enough fat. And then finally, there is an immense pressure to automate. And if you go full scale, the future looks so bright, and it is incredible what you can do with automation. But it is such a difficult task to figure out exactly where to get started with. And it is very easy to waste a lot of money with a solution that you're not happy with. If you start with vision, it just, again, gives you a lot of ammo to make sure that you're making an informed decision that is a little bit less of a risk up front, and you can know exactly how much ROI you can expect to get at the end. So thanks everyone for joining. I hope that you are convinced that you should start with vision, specifically AI vision, when deploying automation. And at this point, I can open it up to any questions that anyone might have.
Yeah, we have one. Is your software able to provide the XYZ location of the defects in the part?
Yes, we can. I don't know if I showed a great example in our software. Let me see if I can pull something up. But we do know the coordinates of each defect and where they are. So let's go into a chicken defect. And let's take a look at this guy. So you can see here that the segmentation is identifying where it is. We know that this doesn't just have fat. The rib meat fat is located here. In here, it looks like we're only exposing length, width, area, and height. This, again, is customizable. We can expose the XYZ coordinates of the fat measurements. Maybe I can pull that up in Recipe Builder. Great question. Bear with me for 1 sec. Yeah, so again, maybe we don't have it exposed here. You can see for the pick, we have the overall pick position of the entire chicken. We're not exposing it here, but if you had an application where you needed to know exactly where the chicken was, like you wanted to talk to a cutting machine on where it needed to cut, that is something that we can provide and expose. Great question.
The next one, how would you treat a food item that is placed in a container rather than loose on a belt?
Good question. We work a lot with bin picking. Really, for us, it comes down to how we want to train that object model. So I mentioned earlier that we can specify the different types of conveyor belts, whether it be blue, whether it be white, whether it be clear. When we're doing bin picking, that is just something we would account for in a bottle. In the model. So instead of generating those pieces of chicken or pieces of corn dropping onto a flat conveyor belt, we would program a box so that it would drop into a bin for like tote picking. What it really comes down to for us is each robot is going to be different. And again, we can interface with a ton of different robots, but you just need to make sure that you have a robot that has the right degrees of freedom to be able to go into the bin. We actually have a lot of different picking strategies that we've deployed specifically for bin picking. Where is it? In our recipe builder, we can go in and see with our sorting, we have this amount collision. And what this is looking at is each product, how much is it touching neighboring products? So when you have stuff in a bin, if one product is touching everything and it's right in the center, it might be very hard to grab because you're going to kind of jam in to the neighboring product. So we can prioritize the ones that have less collision, grab it first so it frees up space or breaks it up, so we can then grab all of them. But I know bin picking is a very challenging problem, but I think it's something that we've sorted out very well over here.
Just a few more for you. Could the system be applied on living plant seedling identification?
Yes, it could be deployed on living plants. We currently have it deployed in factory automation settings. It's not to say it couldn't be deployed there. My guess is that if you're looking at living plants, you probably would need to have the vision system move to inspect other different plants. There is some calibration that goes on when you're programming the vision system because it is using 3D data. It needs to know where the end of the conveyor is so it can start identifying product. So if you were moving it around a ton, that calibration process might be tedious and a little bit challenging, but it's not to say something we couldn't explore.
And the last one we'll take here. Can your software work with most vision camera companies such as Cognex and Keyence?
Good question. So right now we have our own hardware. So the V-Cortex software goes on to the OX hardware, VX hardware, or the TX hardware, which is our vision systems. The current reason behind that is, again, we're using both 2D and 3D vision for not only when we scan the product, but when we're doing inspection too. The 3D data allows us to get all the dimensional information. Um, right now, we couldn't work with Cognex or Keyence, and again, it would be we would if there was a future where we would be deployed on other systems, we would need to make sure that the cameras that we were working with had the right specs for both 2D and 3D. Again, it's not to say something in the future we couldn't explore having our software be hardware agnostic, but currently we're not at a point where we can deploy it onto other systems yet.
And then I know I said last one, but I have another one here for you.
We got plenty of time. Keep them coming.
Is the software able to support multiple part models in the same line but running in batch?
Can it support multiple part numbers in the same line running in batch? Great question. I'll give you a little bit of a loaded answer. So we have one application that is looking at mixed vegetables. So it's looking at peas and carrots. I think the kibbles and bits is probably the closest example I have for that. But we have a mixed vegetable one that I believe can have up to 10 different mixed vegetables. I wish I had a video easy access for you. You know what? Onion rings. Here's the one we want to do. So here, I guess it's not different product, but we're looking at a lot of different defects. We can identify different products. So again, that mixed vegetable one, we have people that have cans of, I think it's peas, carrots, and I forget the third vegetable, but they take this can of peas and carrots, they dump it out, they count all the peas, they count all the carrots. And then if they have too few of one of the different products, they'll add it into the mixing bin to get the right ratio. We can identify this is a pea, this is a carrot, and count them all. We can also, if we were looking at different parts of the bird, identify different chicken breasts versus chicken wings. If you wanted to identify pizza versus a chicken wing, we could build a model that checks that. With each additional unique part that you're doing, there is a little bit of a complexity hit. So it's going to take longer and longer. And we're very far away from the time cost mattering for us, but it does matter at some point if you had 20 different SKUs in there. What we find is that in reality, while a customer might have a mixed line that does chicken and pizza, they're not going to be running them both at the same time. They're going to run pizza for a while, they're going to switch, and then they're going to run chicken for a while. What we would do in that case is in the recipe builder, we can go in and for our detection, right now we're using the chicken object model. We could switch to the corn object model. We could switch to the corn dog object model. So if you were running multiple products, you could have a model for the different products. Maybe you have a model that is chicken and corn dog and corn if all of them were running on the conveyor at the same time. And then you can go into the recipe. And again, we have a recipe here for corn. We have a recipe for corn dog. You could have a recipe that was chicken for Tyson and chicken for Purdue and chicken for Chick-fil-A, and each one might be slightly different, where maybe one customer really cares about the fat trim and another cares about the overall size of the bird. So we can customize based on what the customer needs, but when it comes to creating a model, we try to limit it to only what the camera will be seeing at any one time. And if you're going to be switching foods, we would recommend that you switch the model.
And what would a typical hardware layout look like? Can you access data such as coordinates via EtherCAT?
Great question. So right now, all of the data that we see, so this recipe builder is on the device itself. So we have a vision system, which is a 2D and 3D camera that connects through Ethernet to our VPU or vision processing unit, which is really just a industrial computer that's doing all the compute. That VPU can send this data to the cloud where we can see it on our cloud analytics dashboard. It can also directly interface with a PLC. So if we didn't want to send it to the dashboard, but we wanted to send to an upstream machine to turn the temperature down, to turn off for some maintenance, to stop cutting, whatever upstream system we can do, we can send through either EIP to a PLC, or we can do a discrete I/O connection. We have discrete lines. Right now, we do not have any support for EtherCAT. Again, I don't believe that's on our roadmap right now, but if there was the right opportunity and that was a need, it is something we could explore.
And then we have here, how does the 3D depth sensing and local inference hardware perform in heavy industrial environments with extreme particulate matter, vibration, and highly variable, unfiltered ambient lighting?
Great question. So the lighting question to start, when we are building our object models, we have that physics engine where we can drop all the corn and we're using the synthetic data generation. We can simulate different lighting environments in that. So we are much more robust to different lighting environments than I'd say other vision systems. And if there was a change to the customer where for whatever reason we're not able to detect it and there was such a significant lighting change, we can mimic that in our synthetic data generation and generate a new object model that we could deploy for the customer. You're absolutely right, and I can tell you've been in a food manufacturing space with or automation space in general. Lots of noise, cold, temperature either really hot, really cold, a lot of vibration. We have a stand. We're very easy to slot in. We have a stand that we can deploy right in line. It's a very small footprint, so we typically can account for the vibration with our unit itself. We don't need to mount to anything that really is vibrating. We know that singulation machines exist and they introduce a ton of vibration to get things single. With our system, we can detect overlapping product that's touching and we don't need it to be singulated. So we can encourage people to kind of reduce that movement and that shaking and that singulation system. What was the last piece? The 3D data. Yeah, it's our data has been pretty solid when we've deployed it. We again try to make sure that we're having our models account for various different lighting environments and account for the naturally occurring organic variability. I think that answered your question, but if you have any follow-ups, I'm happy to go a little bit deeper.
Let's see. What happens when you deploy robotics on top of inconsistent or incomplete inspection data?
Great question. So if you have bad data going in, the robot can only work as well as the data that it has. So if you had a vision system that was incorrectly identifying defects and you have a downstream system that is picking out all those defects and sending them back to like get reworked, if your vision system is bad, you've just created a ton more work for your QA team that's doing all the reworks. You've taxed the robot picking up a lot more things than it might normally need to, which just again introduces more areas for failure points. It doesn't just like continue the issue, it starts to magnify and amplify it, because as you automate, the idea is that you can increase your yield and increase your throughput. If the data is bad and you increase your yield and increase your throughput, you just, instead of having a little bit of bad data, you now have a lot of bad data. So it's really good to go in with vision, make sure that the vision system is working and make sure that you trust the data integrity there. Then when you go to automate with full automation, different robots, that problem won't be magnified or amplified.
And assuming we bypass conventional PLC or SCADA systems entirely, what is the exact protocol and latency cost for streaming your raw deterministic classification data directly into a proprietary cloud-synced enterprise architecture?
Great question. So I just want to make sure, I think there's a couple things being asked there. So for interfacing with like enterprising software, right now, all of this data is being sent to our cloud stuff. We have APIs and all of this data you can send to whatever database you want. At that point, you would need to hire a software person that knows how to do that integration and leverage the API. But if you have a team and you do want to do something specifically with the data, that is a tool that you can utilize. What was the first part of this question? Bypass the PLC protocol. Can you repeat that question one more time for me?
Yeah, assuming we bypass conventional PLC or SCADA systems entirely, what is the exact protocol and latency cost for streamlining or streaming
Yeah,
your?
so the latency cost is going to be pretty variable. And again, it depends on how many products are in the field when you're inspecting, how many subparts we want. So if you're looking at a pizza, that's one thing. If you're looking at each individual piece of pepperoni on that pizza, that adds time complexity. And then the total number of SKUs trained. So again, if there's 10 SKUs that it needs to compare against versus there's only 2 to 3 SKUs, all of that time changes. One thing that is novel for us that I guess I didn't mention, so great question. When we inspect, we look directly in the robot pick area, which is very novel. Most other systems image upstream. The reason being is if you image upstream, you have a lot more time to process that image. The downside is that if you image upstream and your little corn rolls over, you have no idea that that corn has moved, and you're going to send bad pick coordinates to the robot when it goes time to pick it. And you might have 2 pieces of corn next to each other, and this one you get the right coordinates and you pick it. And as you pick it, this other one rolls, and now you have the wrong coordinates. Um, so we image directly in the robot pick area, and we have this advanced system where we know when the robot is in the way of the field of view, and we stop imaging, and then it exits the field of view, and we start imaging. And I that time complexity is somewhere between 50 milliseconds to 500 milliseconds, again, depending on how much is going on. But we really are hands-on and work with our clients to make sure that that time is acceptable for their system. If they're going really slow, we can spend a little bit more time processing, ensure that we're absolutely 200% accurate. If they really want to fly and really want to go quick, we can make sure that we're 99.9% accurate if they really want to crank stuff up. But it's a balance of capturing as much information as we possibly can at the speed that the customer needs. But if the customer needs to go faster, we have some tricks that we can do to try to optimize the model.
How is your hardware calculating the depth map for the point cloud? Are you relying on stereoscopic vision, structured light, or time of flight sensors to achieve your value estimations?
Yeah, great question. We are using 3D stereo. So 3D stereo is the 3D part of the system, and then the camera is, I think it's a 3 megapixel RGB color sensor.
Great. That is it for our questions for today. Unless you have anything else, Anthony.
No, thank you so much, everyone, for joining, and this was awesome. Great questions at the end. I really appreciate them.
And thank you to everyone, who submitted those questions. You can register for our next webinar in the Automate Preview Series, Getting Started in Your Next Steps. That happens May 7th at 11 a.m. You can register at automate.org. We also invite you to use the QR code on your screen to sign up for A3's automation newsletters. The next slide, please. Our monthly tech sector newsletters cover the latest news and releases in robotics, motion AI, and vision technologies. You can also tune into the automated podcast with Brian Heater, where he has insightful conversations with leaders in all of our verticals. And you can scan the QR code on your screen or visit automated.fm. And happening soon, Automated 2026 is back in Chicago this year, June 22nd through the 25th. We're expecting over 50,000 registrants and over 1,000 exhibitors for the best showcase of automated technologies. You can register for free using the QR code above or at automateshow.com. And a big thank you to our speaker, Anthony, and today's sponsor, Occipital AI. We really appreciate everyone who came and interacted, and we hope you have a great day.
Thank you so much, too, Jessica, for hosting. And again, thank you, everyone, for joining.